So this lecture is about the three important theorems in Calculus 1. The first theorem that we're going to talk about is called the Intermediate Value Theorem. It's a theorem 2.13 in your textbook. So the theorem says, if you have a continuous functions on a closed interval, let's draw a continuous functions f of x on a closed interval from a to b. Say, okay, I have, this is a and this is b. Okay, so we consider this functions f of x on the closed interval from a to b. If f of a is different than f of b, as clearly this is f of a and this is f of b. They're not the same, right? And then there's a k is any number between f of a and f of b. I just pick a random k in between f of a and f of b. This k right here. Okay. Then the theorem says that there's at least one number c, one values of x, c, in the interval from a to b, somewhere inside, in between a and b, such that f of c equals to k. That means if you project this k to the functions f of x, then you can find at least one value of c here. Okay, so you guarantee to have a value of x, which is c, such that if you apply this value c into the functions, you get to k. Now, what does this mean? So again, if you have a continuous functions on a closed interval, right? And if you pick a value that in between the two ends, f of a and f of b, value any k in between f of a and f of b here, then you guarantee to have at least one value of c, right? Value of x, which is, we call it c, such that f of c equals to k. One of the very useful applications of these theorems is if you're given a functions and you are looking for the zero of these functions. Of the function, the zeros mean is the x-intercepts or is a point where the function equals to 0. If you want to estimate a zero or find some zeros for functions, you can use the intermediate theorem in order to do that. And again, if you have a very nice functions that is very easy to solve for an x-intercepts, then there's nothing to say, right? But if you have an ugly functions like this, y equals to e to the x plus l ln x, okay? So if you want to find the zero of this function, you set y equals to 0 and you're trying to solve for x, but because this function's involved in exponential functions and is also involved in logarithmic functions, it's kind of hard to solve for the zero algebraically. But luckily that we have a theorem, so then we can use this theorem. We can utilize the theorem in order to estimate for a zero of these functions, all right? So now if you look at this graph of these functions here, you can see that, oh, I see the zero is somewhere in between 0 and 0.5, okay? But then how can I estimate, how can I have a good estimations of what that zero is? Well, I look a little closer, okay? And I can see that here, if I start at, well, if I look a little closer, then the zero should be in between 0.2 and 0.3, right? It's somewhere in between 0.2 and 0.3. So I call, by looking at the graph, I set my closed interval is from 0.2 to 0.3. And then I start at x equals to 0.2. See what happened here. 0.2. If I put 0.2 into the functions, the y value is a negative value for sure, right? You can see the points here. If I go to, if I move my points closer, right? Move my points closer to the actual 0. So I move a point to the right, which is 0.25. See what happens? 0.25, I still have a negative value. All right. And then I go a little closer, so 256, still have a negative value. If I go to 0.3, now, as you see that if I go a little too far from 0.256 to 0.3, my y values go from negative to positive. So that is where I'm like, okay, so using the using the intermediate value theorem, I can say that since the functions on the interval from 0.2 to 0.3, it goes from the function values goes from negative to positive, right? Because if you plug 0.2, you got a negative value. You plug 0.3 into your x, you get a positive value. So using the intermediate value theorem, if k equals to 0, right? Because we're looking at the 0 value for the functions. If k here equals to 0, then I guarantee to have a point of x, right? A value of x in between 0.2 and 0.3, such that f of c, right? F of x equals to 0. And if f of x equals to 0, then that point is actually the point that I'm looking at. All right, so 0.3 is positive, which is a little too far, right? Then I scale back a little bit. So I put 0.258. It's still negative, good. So, and then I go a little bit further to 6, still negative. 0.265, still negative. Negative 0.268, still negative. All right, 0.27. Now is a positive value. So if you look at these two values here, you can see that if I go from 0.268, I still have a negative value for y. And if I move to 0.27, I have a very small positive value. That means my 0, the actual 0, the 0 that I'm looking for, is in between 0.268 and 0.27. So I narrow down my interval to 0.268 to 0.27. Based on this table, it goes from a positive value, right? Negative value of f of x go to positive value of f of x. So then using the intermediate value theorem, I guarantee to have a values in between in this interval here, such that f of c equals to 0, because 0 is in between a negative value and a positive value. So this is a technique that helps you find helps you estimate a 0 of the functions using tables of values, right? And then you know where to look at. You look at the values, right? The two x values where the functions go from negative to positive, or the function goes from positive to negative. And the narrower of your intervals, the better of the estimation that you getting at for the 0 values. Okay, so that's an applications of the intermediate value theorem. Next, in chapter 4, we learn about the another two theorems. The first one is the Rolle's theorem, and the second one is a mean value theorem. These two theorems are related closely to each other. Actually, one is just the broader case of the other. All right, let's start with the Rolle's theorem. So the Rolle's theorem says, if you have a continuous functions f of x on a closed interval, again, we have a continuous functions f of x on a closed interval. So this is x, y, and I draw a functions f of x, just like a random functions. Okay, so this function is continuous on the closed interval from a to b, and is also differentiable on an open interval from a to b. So it's differentiable means the derivative, you can find the derivative of these functions at any point in between a and b. Okay, so there's two conditions that we need to satisfy. First is continuous continuity, second is differentiability. Okay, the third condition is if f of a equals to f of b. What does that mean? That means the a and b are the points where the function values are the same. So let's pick 2 points, a here. So you have f of a, right? And then another point b here, f of b. So let's write it right here. F of a equals to f of b. All right. So if these 3 conditions satisfy, then you guarantee there's at least one value of c in between a and b such that the derivative of c equals to 0. Okay. Again, if the function is continuous, the functions is differentiable on an open interval from a to b, and also the function value of at a is the same as the function value of b, then you guarantee to have at least one value of c, right, value of x, which is we call it c, in between these 2 values a and b, such that the derivative of f at c equals to 0. What does it mean when you say the derivative of a function f at a point c equals 0? It means the tangent line at the point c here, tangent line at c, is a horizontal line, right? When the derivative equals to 0, it's a horizontal line. If it's horizontal lines, then it's gonna be such a line like this one. So if you look at the function f of x from a to b, you have this point here where if you wanna draw a tangent line, it's look like a horizontal line and actually a horizontal line. And also you have another horizontal lines here. So in this example, you have 2 value of x at which the derivative of the function equals to 0. Okay, and if there's exists a point at which the tangent lines is a horizontal line, that point is actually a local minimum or a local maximum value of the functions. We learned this in the previous sections. Okay, so this is, as you say, that this is the relative max, and this point is the relative mean. Okay, so this what does this theorem tells us is it tells us that if you have a continuous functions on a closed interval, if that function is differentiable, right, and the function values at a and b are the same, then you guarantee to have at least one local extrema. It can be a relative maximum or it can be a relative minimum. So you guarantee to have at least one, but you can have multiples of the relative extrema depending on the functions. Great. So now we can, let's try to do a couple of examples related to the Rolle's theorem. So example number 4. You are given 2 functions on 2 different closed intervals, and you want to use the Rolle's theorem. But before you can use the Rolle theorems, right? The Rolle's theorems helps you to determine whether the functions has a function has a relative extrema on a closed interval or not. So before you can use it, you need to make sure that the functions and the intervals satisfy all the conditions that we need to have. So first, it has to be continuous. Second, it has to be differentiable, and third, the endpoints, the function values at the endpoints have to be the same. Okay. So look at the first functions, f of x equals to negative x squared plus 3 of x. This is a polynomial, so this functions here is continuous everywhere, for sure. So for sure is continuous on the interval from 0 to 3. Okay, so that's the first conditions. Second conditions, this is polynomial functions, and the derivative of this function is also another polynomial function. So the derivative is defined everywhere. Third, f of x is differentiable on this closed interval. So the two conditions satisfy. So the last condition is, does f of 0 equals to f of 3? Okay, so f of 0 should be equal to 0, and f of 3 equals to also 3 squared negative 9 plus 9 is 0, 0. So f of 0 equals to f of 3, that's the third conditions. Based on these three conditions, you can say that we can use the Rolle theorems, right? Rolle's theorems can be applied. All right. Well, I'll go to the next functions. So the next function is x to the 2 over 3 minus 1 on the closed interval from negative 8 to 8. So this functions here, as we know, that is continuous everywhere, right? Because there's no restriction for x. So f of x is continuous on this closed interval because it's continuous everywhere. How about f prime of x? So f prime of x is gonna be 2 over 3, x to the negative 1/3, right? And x to the negative 1/3, remember, we can move it down to the denominator, okay? If it's moved down to the denominator, that means this function's f prime of x is not defined at x equals to 0, okay? So that means the function's f of x is not differentiable at x equals to 0, and x equals to 0 is in this interval. So this second condition is not satisfied. So we can, if one of the conditions is violated, we can conclude that the Rolle's theorem cannot be applied to these functions on this particular interval. So conclusions is Rolle's theorem cannot be applied. Okay. Okay, the next theorem is the mean value theorem. What does it say? It says if the functions is also, if you have a continuous functions on a closed interval and also differentiable on an open interval from a to b. Let's draw that functions, x, y, okay? And then you have a functions here, f of x here, okay? And I just pick two random points, right, for my interval from a to b. This is a, and this is b. Okay, so I have f of a here, and I have f of b's right here. Then what's next? Then there exists a number c in the interval from a to b. So there exists a value of x, which we call as c, in this open interval from a to b, such that f prime of c equals to f of b minus f of a divided by b minus a. What does that tell you? So look at the right side of this equation here, f of b minus f of a over b minus a. This is actually the slope, right, of the line that goes through the point a, f of a, and b, f of b. Okay, so that's the right side of the equations. What about the left side of the equations? So the left side of the equation, f prime of c, it's just the slope, right? It's a derivative, so it's slope of the tangent line at x equals to c. Okay, they both represent for slopes of some lines. Okay, so we look at the right side. We know that the right side of the equation is the slope of the line that's go through these 2 points. So we just need to draw a line that goes through these 2 points here. 1 point, 2 point, this line right here. All right. And if the 2 conditions are satisfied, then we guarantee to have at least 1 point in between A and B such that the tangent line at this point is the same, is parallel to this line from this point A to B here. Okay, so that's what it means. So let's look for that point. So we want to find a point where the tangent lines, maybe this point right here. And if you draw a tangent line to this point, it looks like it's parallel to this gray line, right? The line that goes through A and B. So I found this C, 1C. So you guarantee to have 1 point, like 1 point where the tangent lines is parallel to this secant line. However, you can have more than 1 point. Let's find if let's see if we have another point here. See. So I just need to have a ruler here, and then I go parallel. Maybe this point, or maybe this point. This point looks promising here. So if you pick this point and then you draw a tangent line, right? It goes through this point. The tangent line is parallel to this line. So you found another point. Then there's more than just 1 point that satisfies this mean value theorem. Okay, again, the mean value theorem tells you that if you have a continuous functions on a closed interval, and if that function is differentiable on an open interval, like same interval but open, then you guarantee, or there exists a number C, right, an x value in the closed interval, in the open interval from A to B, such that the tangent line, the slope of the tangent line at that point C is the same as the slope of the line that goes through the point A and B. Again, A and B are the endpoints of the closed interval. Well, let's look at the next example that will maybe illustrate how to use the mean value theorem. Okay. Let's consider the functions negative x squared plus 5 is a parabola, as we know that. And this function here is continuous everywhere, and it's also differentiable everywhere. So the first 2 conditions of the mean value theorems is already satisfied. All right. So that's what we know. So let's write it down. So f of x is continuous everywhere from negative infinity to positive infinity, and f of x is differentiable from negative infinity to positive infinity. So the 2 conditions are already satisfied. The first question is find the equations, right, of the secant line joining the 2 points, -1, 4, and 2, 1. So this is a simple questions. So in order to find the equation, you need to find the slope. And the slope is just f of b minus f of a divided by b minus a. So I take 4 minus 1 over -1 minus 2. That will give you 3 over -3 is -1. Okay. And now you're going to use a point slope form to find this line. So y minus, just pick one point. I pick the first point, minus 4, which is the y value, equals to -1, which is the slope, times x minus x1, which is -1. And if you want to simplify this, it's going to be -x, +1, -1, -1 plus 4 should be +3. All right. So I found a secant line that goes through these 2 points, right? Now use the mean value theorem to determine a point C in the interval from -1 to 2 again. So we pick these 2 points, and then the x value of these 2 points is -1 and 2, such that the tangent line at C is parallel to the secant line. Why do we need to use a mean value theorem? We need to use a mean value theorem because we need to know the existence of the point C, okay? Because f of x is already continuous on this interval, it's also differentiable on this interval. By the mean value theorem, there exists a point C on this interval such that the tangent line at C is parallel to the secant line. So the mean value theorem guarantees us a point. So then now we just need to find it. How can we find this point? So we know the slope, right? The slope of the secant line. And if the tangent line at C is parallel to the secant line, that means the slope of the line that we're looking for is the same as the slope of the secant line, which what we found up here is -1. So we know the slope is slope of the tangent line, right? At C is -1, okay? We need to find the point C. How can we find point C? But we know the slope of the tangent line is C, and how can we find the tangent line, the slope of the tangent line of a functions? Well, the slope of the tangent line of the function is actually just the derivative of the functions. So then that means we need to find the derivative of the functions f of x. Simple enough, we just use the power rule. So the derivative is -2x, okay? So the slope of the tangent line is -2x, right? And we know that it's equals to -1. So we just set it equals to -1. Then we can solve for x equals to 1/2. So if we know x is 1/2, right? Then this is actually the point C here. And if x is 1/2, then we can find f of 1/2 is -1/2 squared plus 5 should give you -1/4 plus 5. That should give you 19/4, okay? So you found C is a point where the x value is 1/2 and the y value is 19/4. So at this point, on this function's -x² plus 5, the tangent line at this point is parallel to the secant line that goes through -1, 4 and 2, 1 here. Okay. And we can find the C. We know that this point C exists due to the mean value theorem. Okay, the last one is find the equations of the tangent line go through C. So we know the slope is -1. We know the point is this. We can just find the line by using point slope form. y minus the y value equals the slope times x minus the x value. Okay. And if you want to simplify it, you can actually simplify it. So it's going to be 1/2 plus 19/4. So then y will be equals to negative 1/2 plus 2, 4, 4, 2 plus 19 should be 21/4. All right, so this is the line, right? The equation of the tangent line that goes through this point here and is parallel to this, to the secant line that goes through these 2 points here. Okay, next example. So the next example is ask you to find. So if you have a functions f of x, and that function is continuous and differentiable on the closed interval from 2 to 10. So these 2 conditions here already satisfy the mean value theorem, okay? So that means if you have these functions, you know that there exists a point in between 2 and 10 such that the derivative of that point is equals to the slope of the secant line that goes through these 2 points. Well, but the question is, if the function value at 10 equals to 10, and we know that the derivative of the functions f of x is at least 2 at every point in this closed interval from 2 to 10, then what is the maximum value of f of 2? What does it mean? You have a functions, right? Just, I don't know what exactly this functions is, but I know that the functions is continuous and differentiable from on this intervals from 2 to 10. I know that f of 10 is 10 right here. Okay, and I know that the functions, the derivative of the functions on this interval is always greater than or equals to 2. So it's at least 2. It's always greater than 2 or at least the same as 2. Then what is the maximum value of f of 2? So this is f of 10. What is the maximum value of f of 2? F of 2. Okay. All right. Well, let's see. We know that the function is continuous and differentiable, so then we can use the mean value theorem, right? And the mean value theorem say there exists a C such that it's gonna be equals to f of 10 minus f of 2 divided by 10 minus 2. Okay, there exists a C that the tangent line has a slope is the same as the slope of the secant line from at 2 and 10. But then another information that we have is the derivative on this interval of the function of this interval is always greater than or equals to 2. Okay. So from 2 to 10. Then we have an inequality. And we have some information for some of the pieces in this inequality, and we hope to solve for f of 2. Here we go. F of 2. There's this question mark on f of 2. Do we know f of 10? Yes, it's 10. F of 2? No, I don't know it. Do we know 10 minus 2 equals 2? Yes. Then I just need to solve for f of 2, right? So we have 10 minus f of 2 is greater than 16. Then 10. Oh, so now I can solve for f of 2. So I can bring the f of 2 to the other side and bring this to this side. So I have 10 minus 16 is negative 6 greater than f of 2. Okay. Finally, I got some conclusions, some restrictions for f of 2. Is say f of 2 is less than or equals to -6. If f of 2 is less than or equal to -6, that means the maximum value of f of 2 is -6 is your answer. Okay, it has to be less than or equals to -6. That means the maximum value of it is -6. All right, so I want to show you that this theorem is pretty famous theorem, and why it's famous, and it's why it's very important theorem in calculus. Let's go to China. So in one of the bridges in China, I think it's Belgium, China, they do have this theorem that is printed on this bridge here. Okay, and then you can see that this is one of a very big bridge on a very like heavy traffic sections. Okay, and this theorem is important enough for everyone who like travel through this segment of the city will see it every day during the commute. Go to work, go to school, go to eat. So they always see this theorem almost every day in their life. That's why it's a very important and famous theorem in calculus.